Alright, let's take a look at math refresher on calculus. Why is calculus important for machine learning? Well, remember we did the housing price exercise, regression problem, where my friend asked me to predict the price of his 350 square meter house. How did we do it? Well, I did some research and found that there were 6 houses sold in the area of my friend. And I would use that to draw a linear model. So I decided that it should be a linear model. So we tried to fit a line through these 6 points, but it didn't work. Yeah? There's no way you can put one line through these 6 points. So we decided to take the best line. And then we defined the best line as the line where these vertical blue lines here, when we add them all up, where this should be the minimum. Yeah? So we define a cost function with W and B. It's a linear relationship. It has 2 parameters, W and B. And we developed the small lines here is the predicted value minus the true value. We squared and we divided by the number of samples. And we call this the mean squared error, and that's a cost function. That's the penalty we pay for not being able to present reality 100%, which is the case here, okay? So, it's obvious that we want to minimize this cost function. Once you talk about minimization and functions, you talk about derivatives being set to 0. Yeah? So that's why we will have derivatives here. We will have how can we find a minimum of a function? How do we deal with derivatives when there's many parameters? So partial derivatives. We'll define the gradient vector and the Hessian matrix. We will also look at how do you find a minimum of a function with constraints? And last but not least, Taylor series. Taylor series allow you to approximate any function by polynomial, yeah, near a certain point. But more about that later. Okay, now so let's tackle the first one, derivative. Yeah. Basically, a derivative is the rate of change of a function, or you could say it's the slope of the function. I've drawn here an xy grid and I drew a straight line. Yeah. And the rate of change means I take a step delta x here and I see what my corresponding step delta y is. Yeah. So the slope is delta y divided by delta x. And wherever you wanna make this calculation, this will always be constant for a straight line. Now, here we have f of x again. What if we don't have a straight line? So you see we have a curved line here. If I try to do the same and connect these 2 points, yeah, this is the line I will get. What's the problem? Well, the problem is that in each of the points between a and a plus h, the slope will be different. Yeah? Here the slope is like this. Here the slope is like this. Yeah? So basically we could write that the slope is still delta y divided by delta x, and in this case this is delta y is f a plus h minus f of a, yeah, and divide by delta x, that's a plus h minus a, yeah. But we need one more thing. We need to take the limit for h going to 0, because when h is going to 0, I find the instant rate of change in a f of a. So a derivative we write like this, df with respect to x. Also sometimes we call it f prime of x. Yeah? And that is the instantaneous rate of change. Rate of change in the point A f of a. Yeah? That's the definition of a derivative. So df divided by dx, or f prime x. Now how do we find a minimum? Finding a minimum of a function is quite easy. You take the derivative and you set it to 0. For example here, f prime of x, the derivative, equals is 2x. The 2 moves to the front and I deduct 1 here. Yeah? So if x if f prime x equals to 0, means that x must be 0. Yeah? If 2x is 0, means x is 0. So x of 0 is your extremum, but you don't know if it's a minimum or a maximum. But if you're going to take a look at the graph, yeah, you see that the slope on this side, the slope is negative. So df over dx is negative. When you look at the other side, yeah, the other side, the slope is positive. df dx is positive. Yeah? So here your slope is going to be negative, here your slope is going to be positive. So you go from negative to positive, which proves that x is 0 is a minimum. Yeah, it's just as simple as that. Now let's take a look at another example here. Okay, we're gonna derive this. F prime of x equals 3x squared minus 1 times 2x. Yeah, the 3 comes to the front, and then we leave that, we subtract 1, and then we derive this between the brackets. Yeah? So when is this 0? Well, it's gonna be 0 if x is 0. Oh, sorry, here must be a square, sorry. Or if this term is 0, so that means x squared is 1, so x could be plus 1, and x could also be minus 1. Yeah? So these are the 3 extreme points that we find for this function. Minus 1, 0, and plus 1. Okay, so let's see what it means. So let's go, if we look at the negative numbers here, this between brackets is squared, so it's always positive. So it's the 2x that's going to define the sign. Yeah? So if x is negative, this will be negative. Yeah? It will even go through the minus 1. When x is positive, everything is positive. So what you see, you go from minus to positive, so you will have a minimum here. Huh? You will have a minimum. Here you stay negative, so here you will have something flat and then go up again. And here you have something the same and then go up again. Yeah? It's flat because in minus 1 and plus 1 the derivative is equal to 0. So here we have one minimum.